less on oxygenation and other things, but on the balance, sometimes the acid-base balance, which is one of the major things that the respiratory tract does. But thinking also about the overall sort of anatomy of those systems, where things can go slightly wrong. In the case of gas exchange, this idea or this knowledge of where exchanges occur, the biophysics of it, the idea that you can have, or the lungs, for example, we mentioned, very, very, very sensitive to inflammation for a good reason. And in the case of today, we're going to start with the endocrine part and digestive. The digestive, you'll see that when we start talking about the digestive system, think also about this anatomical structure. It's going to be this highly exposed system, because it is by far the highest exposed system, because in one, you're inhaling air. The urinary tract, not necessarily that it has, it is somewhat exposed, but theoretically it has only one direction of exposure. In the case of the digestive system, the thing is that you are putting water and food inside of you. Some of the people, they say that, the digestive system is almost the system that is inside of you and at the same time is outside of you. And it is true. Everything that is in non-digested is not necessarily inside of your blood and stuff. It has a big barrier, and you're going to see this is the angle that I think I would like you to pay attention on the digestive side. But before that, I wanted to touch, I don't know, we could start in both, either the endocrine or digestive, but we're going to go through the endocrine first. It's just as a part where, and at some point I'm going to ask you to, I have a little table there with lots of these hormones and what systems and so on. And I put it there before, and I think it was not long ago when I included this portion of the endocrine system. Obviously, endocrinology is a course on itself, and it could be even within each system is a course on itself. The thing is, some of the basic premises, the same way that in the cardiorespiratory, the biophysics of it is important, the idea of pressure is important, the idea of, when we talk about dehydration, or when we talk about ventilation and carbon or control of the acid base, in the endocrine system, a few things that are common knowledge or should be common knowledge will be addressed here in the first slides. One is that, of course, you do have things being produced, especially by your brain, hypothalamus, pituitary. Eventually, it will be produced by a series of organs that goes from the lungs to kidneys to the liver to the adrenal gland and to the reproductive organs. We're not going to touch base on repro, of course. It doesn't make sense for us, but it is all produced in very small amounts that goes from one organ to a target organ, and that produces a certain effect. Okay. The endocrine system, and in some ways, we should have put it here, a neuroendocrine system. Why? Because the two systems are very often integrated. Okay? So, for example, let's go and and we ask ourselves, what is a hormone? The control systems, the need for vasculature or the blood transport. But let's think on, and when we go, for example, to talk about diabetes later on, it has in humans, it occurs in humans, it occurs in domestic animals, and that side of disorders has little to do with these major biophysical things that we were talking in the cardiovascular side and in the respiratory tract. that has to do with very simple and very specific actions of some of the hormones. The reason why we go very general on the endocrine is that for this class, the most important thing is that you have a very general view. And sometimes, you know, it was a little bit of a challenge for me when I structured the class, is that people ask me, but you're going to cover all these things, so you need to have a lot of requirements for the class. Because at the end of the day, we cover a lot of stuff in physiology. We're going to cover pharmacology at some point. We're going to cover a little bit of pathology. But the idea is that you have the minimum of the base in order to construct cases in your head. And that's why some of the clinical cases and the other things, they tend to be rather simple. When I say simple, it's not because it is unimportant or anything. It is just that we focus more on the primary changes, acute changes. We do not go into chronic, super delicate house type of diseases that you need a detective to find. It is not that. It's that you have the ability to integrate different systems. So all of this, if it is a true endocrine, paracrine effectors, neurotransmitter, exocrine effect, and you have also autocrine effect, all of those things will have some importance, especially in your specific cases, in clinical cases, because eventually, and this is very important, especially these two here, when we start studying, for example, the immune system, paracrine and autocrine effects, the immune system is this very complex, complicated, really, system in terms of control that depends on and really interacts with the external environment and external agents, which is indeed very different than on most of the other systems. So all of this will be important. For us, I think, the classic definition of endocrinology is that, yes, something has to be produced in one cell, transported in the blood, act on a different cell, and so on. So, and obviously, in the previous slide when we talk about exocrine effects, is like talking about, I think the classic example would be the digestive tract, that you produce something that will act on the food, so it's liberated into the lumen of a certain organ, so it doesn't go necessarily affect another organ. No, it's going to affect a product, in this case, food. That's the classic example of exocrine. So, for a lot of the changes that we do that happen or is controlled by the neuroendocrine system, some of these examples, such as stress response, which we're going to have a class only on that, and for example, the milk letdown, those are true examples of the combination of the two systems. In the case of the milk letdown, you basically need the stimuli or the stimulus of the mammary gland or the teat of the mammary gland in order to have a neural stimulation going from that end of the mammary gland towards your spine, from the spine to your brain, and in your brain producing something that will return to the mammary gland and let the milk down. Okay. Some of the other ones, such as direct response in these stress responses, for you to have a stressful response, pain, or sometimes not even pain, what you hear, what you observe, so emotional change is already enough to trigger a very potent endocrine response. So basically, your ears, your eyes, your smell, all of that can, for example, trigger fear. You see a bear in front of you in the middle of nowhere, you get stressed. Okay? Nothing physically affected you, but you feel stressed. So it's an emotional response. All of this, and this is the part where reproduction here for us, going back to the physiological functions. We tend to, in those cases here, to go, especially growth and reproduction for domestic animals especially, those are big, big topics. Why? Because they have economical importance. For us, the metabolism, and to a certain extent here also the immune system and the stress response, those will be the two major categories. So you can add in your notes there, not only metabolism, but the immune and the stress response will be the two major categories in which we will work on. Why? Because lots of the clinical cases that we'll deal with will go into that direction. For example, we tend to go and try to classify, for example, some of these changes into autoimmune diseases, metabolic diseases, infectious diseases, for example. Those are categories of disease that they have very specific characteristics, and they will follow on more on that. Can we have a case on growth and reproduction? Absolutely, we can. But they will tend to be more tied with these other 3 or 4 categories that I said. Why? Because they tend to be more integrated in nature. They tend to put more systems together, and you have to have a good rationale in order to solve, the whole case. Energy and mineral, in this case, is the part that, before I mentioned to you the case of the acid-base balance, carbonic acid. Okay. So that's a typical example of, at the end of the day, triggers a very strong mineral response. So, for example, in some ways in your body. Go back, always think about this. The very first class, when we start asking things about, very simple things about water, pH, but electrolytes, and what is temperature, what is the effect of these things. It is at the core of some of the things that you end up seeing in the class. It is very important that you understand those basics. So the next slide, then, we can spend some time, talking about some of these things. Energy, mineral, as I said before, growth is also important, but even this one here, for example, insulin can easily be on energy. Reproduction, I made the table here with all those hormones. You won't need for that. We might need, or we might go into some of those cases, mostly if we have a case scenario, but most of the case scenarios that I tend to save is actually for the other class. It makes a lot more sense. But for us, we have to think these two. Now, for those two, think about those names over there. Insulin, glucagon, cortisol, epinephrine, norepinephrine as well. Thyroid hormone, perhaps, is one that is also important, not only in growth, but also in energy metabolism. On minerals, parathyroid, calcitonin, angiotensin, renin. So those things will eventually, and all of those that I think I mentioned so far, you're going to have some basic knowledge on those. Okay? The idea here is for us to go in very detail on the slides in each of them. No. For that, you can go to any book and give it a good read in each of the, of these hormones. You go, for example, in that physiology book that is on the syllabus. It is enough. It's not an extensive reading, but it's a good thing to, part of this class is also to go back to certain things that you have already learned. Go back a little bit, come back to the class. It works a lot well, and we use the time here for more interesting things. Okay. So, but let's go and say we go very, very quickly in one of those, because the other the other parts of this class is really on the basics, on how the endocrine system works. So we might go rather quickly, and we can spend a bit more time on some of this. Insulin, glucagon. That's something that, okay, like very, very high level thing. So it deals with a lot with glucose control. Okay. So if you go cortisol, cortisol also deals with sugar control as well, but it's also the major hormone related to stress. And that's the part that later on we're going to have to dissect. When we say stress, stress has to mean something to you. Stress has to mean more than just say, oh, it's stressed. From a body organism point of view, what are the changes that stress causes into you? And there are different forms of stress. You have chronic stress, you have acute stress, and they are very different. Okay? So when you talk about this guy, and epinephrine as well, these two are stress-related hormones. They affect energy metabolism, for example. What is your take? Would stress-related events affect energy metabolism? They almost have to. Okay? So give me an example. Give me an example of how stress alters energy metabolism. Excellent. Very, very good. So one form of stress in this case will probably have to trigger, increased consumption of energy. You cited, for example, cold stress. If you're talking about, for example, emotional stress, the rationale is almost the same. When you saw the bear, what do you want to do? Run like crazy. Okay? And for that alertness brings a lot of stress and a lot of energy consumption. Okay? Another thing is like when you go into a stress, for example, provoked by an infection. You're going to change a little bit, although it's not necessarily the same mechanism, but you're going to change what? The consumption of energy from your immune system. And you say, but your immune system, well, when you're sick, you consume, your cells from the immune system consumes a lot of energy. I mean, a lot of energy. And so stress and energy, they are almost always tied together. Okay? When it comes, for example, on the mineral metabolism, and this is the part where the fine-tuning of the last class when we start mentioning all these changes on pH and stuff, the thing is, what I want you guys to change in your heads is that all of this is somewhat mineral. Okay, so when you talk about pH, not necessarily mineral in the sense of calcium or magnesium, but you're talking about, I think the way I prefer to see that, it is on balance, electronic balance around your body. Okay, in order for you to achieve that, you play with minerals. The thing is, some of your organs require more of a certain mineral than another. So it is really like a ballet of changes that occur in your body, and you try to somehow control. So if you think about, for example, calcium, which is related to those two first, parathyroid hormone and calcitonin, you obviously have to see that, why would you need calcium? We're going back to very simple very simple concepts, on this. Talking about stress, I want to dissect stress. I'm going to some of those minerals I want to dissect. So first of all, when this pops into your mind, calcium, what do you remember in the body? The bones. So your bones are actually a very, very dynamic organ. Very fluid. Not fluid in the sense of, it's pretty hard. But what else your bones are made of? Why do I ask you that is because, later you're going to see that even that is related to your acid-base balance and other. What else you have in your bones? What are your bones made of? Or another, probably, major mineral. Phosphorus. Okay, phosphates. Lots of phosphorus also in your, and these are two major minerals that will be necessary for a bunch of functions in your body. Give me one example of why calcium is important. Anything. Muscle contraction. Need lots of calcium for muscle contraction. Oh, but it's, who cares about, remember when I said before, sometimes if you have problems with muscle contraction, it's not that you don't, the problem is not you lifting away from your chair, it's you breathing. That can affect something else. In case of phosphorus, what is one of the major functions of phosphates, for example? There, Gatorade has it probably. What is one major function of phosphorus? Phosphates. It's also a big, big buffer in your body. Okay? An enormous, a really, really strong way in which you buffer your system is through that. Now you go and have here, for example, mineral metabolism. We go here, angiotensin, renin. We'll go into the renal side of it, but that has to do with also some of the other controls like renin, angiotensin, aldosterone. Aldosterone, the name, for example, of this hormone is. The classification and category of this hormone is on the mineralocorticoids. Is a corticoid, very similar to cortisol, but it changes the way you release or uptake minerals, especially in your kidneys. Okay? So your body will have to dance through this. On top of that, you're going to know that some of these changes. Some of these minerals, so as I said, calcium will be important for muscle contraction, then it will be important for respiration. On the other side, sodium, for example, will be controlled by this renin-angiotensin, which controls also the amount of water that you retain in the body. That can also affect pH, depending on how much dilution of things you have inside your body. So you see how these things start to mash together and stuff. So although the class eventually becomes boring, the idea is that pretty fast we start with case studies for you to try to go more in depth about the changes that we're talking about. So so again, is it worth going and obviously, when it comes to the case studies, 100% sure, anything that is related to that case, go back to the physiology book and try to understand the basics. But also, for some of those, it's already a good head start. Go and take a look. Go and take a look. Go back and take a look. We're not going into the complicated part of it, how much is produced, but the idea that you know roughly where things are, it is super important. So that your kidneys will be very responsible for doing certain things, that your liver will have to do this, that your hormones there, some of them is going to be in the thyroid, some of them in the parathyroid, some of them in the medulla of the adrenal, some of them in the cortex of the adrenal, pancreas, So you see, this class is very slow, but the stuff is that the idea is that you really start thinking about those things together. Really, really, really. So let's go, the next few parts is really like, you don't need to know much of these. You already know he has produced in very, very small amounts. Steroids, I know a protein molecule activates. It's very, very dependent on enzymes. Amplification, of course, those are things that are produced in very, very, very tiny amounts. Nanograms, 10 to the minus 9, 10 to the minus 12 in terms of concentration, so not a big deal. And this hormone action versus the nervous system action, you'll see that one is more responsible for long-term control. The neural control tends to be more immediate, for something that you need right away. That's why, for example, cortisol and adrenaline, they are both part of your stress response. Always the first one, especially in acute situations, tend to be adrenaline. You have this wash of adrenaline in your body, and it is normally triggered by your sympathetic nervous system. Okay? So whatever you see, whatever you smell, it goes straight from there to neural systems that are right next to the adrenal gland that have direct neurons attached to the medulla, and that explodes in the amount of adrenaline that you produce. Okay? The other case is going to take a few minutes or hours. It's going to go to your brain. It's going to produce corticotropin-releasing hormone, adrenocorticotropin hormone, cortisol, that will give another stress response. One's very fast, one is very slow. Not necessarily slow, but it takes a little longer. All of these things, I mentioned this in some of the previous class, for example, on the reproduction. These classes of hormones, I'll tell you what this will be important for. It is eventually major functions from some of these hormones that I mentioned before, mineral, energy, and then eventually immune system, stress. So a bit of the function, a bit of the anatomy, where things are, where it's produced, and so on. And then it comes the other part that is probably the most important part, is the transport of this. And when I say the transport, it's going to have to go from one place to the other, and depending on the nature of that molecule, will be dependent on proteins to be transported, or will be dependent on certain, or how it's going to be metabolized. It's going to be in the liver, it's going to be in the kidneys, it's going to be in the lungs. So all of these extra things that the hormone is dependent upon to work will be somewhat tied with the structure of it. So if you talk about proteins, such as growth hormone, insulin, ACTH, not so much, or oxytocin, this peptide enters a little bit in the class of hormones, but of proteins, but they are just smaller, more simpler, and some of these amines like dopamine, melatonin, epinephrine, this here tends to be, for example, very tied with your central nervous system. Okay? Even the communication of it, production by the hypothalamus or production as neurotransmitters, they are in this type of class of hormones. This one here is steroids, and also the next one, which is, proteins, and the next one, which are steroids. Those tend to be the ones that we deal the most in some of these cases. First of all, one is proteic in nature, amino acids and so on. The other one is fat in general. So if it is a fatty acid, if it is a cholesterol-based hormone, they tend to be, as opposed to what we, for example, what we mentioned in the 312 class, the idea here is that you truly understand that they are transported in different ways. They have to be transported. One of them is fat-like structures, like cholesterol. They need to be transported down to something. Why? How do you transport fat in your body? You call your mom one day, "Hi, Mom, I went to the doctor, my cholesterol is high." How did they measure that? Oh, there is a simple thing there, you know, how to measure that. Yes, it has to be, for example, you have heard about good and bad cholesterol. How do you determine what's good and what is bad if the molecule is the same? It comes down to how it is transported. That's where I'm coming. That's where I'm going with this. So go back to this stuff no, I'm not talking about the function of these things. I'm talking about how this is, what is the dynamics of it in your body. Transport, excretion, metabolization, this is all important. This is all super important. Where we're going to use some of this concept of where is excreted and where is metabolized is when we go, for example, into the little couple of classes on pharmacology. We're talking about antibiotics, anti-inflammatories. Very important that we understand where and how these things get out of your body. Why? Because they can be toxic to the liver. They can be more toxic to the kidneys. The other day I was listening to all these stories about former NFL players that played football through pain and lots of surgeries and stuff, and somehow the only way for them to play is to be taking a very potent anti-inflammatory. What happened to these people after a while? Their kidneys shut down. Why? Because that thing, how it is excreted, is what kills you at the end. So the idea to know a little bit of this, the context of this, is not that you say, oh, there's a low density lipoprotein that produces cholesterol, and that has a lot to do with the mitochondria, and da. No, that's important, but this is not the function of this class. The idea for the class is that you have those things in mind. So for this class, it's important that you find that it's interesting or very important metabolization of these hormones, function, localization, how that metabolizing and excreting some of that is super important for the cases where you're going to talk about. Now, the idea there, when I told you, how do you transport fat inside of your body? It is, I'm 100% sure you have had something about this during this 4 years that you are here at UBC, been in Biochem 101 and so on. But the idea is that in general, they are giving maybe the first couple of years, and very much you're interested in the very true biochemical part of it. Okay? And now you're going to have to bring that thing back a little bit to this. Now, so I'm going to ask again, how do you think fat would be transported? It's in this slide. So how do you think that's, and why?
Is it in the membranes? And does it form droplets or membranes? So.
Yeah, so this is why it cannot be transported freely. you form those droplets, and those droplets do what in water? Hydrophobic. So they don't mix. From a scientific nomenclature, they're not soluble. Once they're not soluble, the problem with everything that is not soluble goes back to your cardiocirculatory class. You tend to have very, very big problems of transporting things that are not really fluid in plasma. Why? That thing can promote even like damage in your vessels. You can clog stuff. Can you imagine after a good barbecue, lots of these little droplets running around your bloodstream? You're gonna have physical problems dealing with that. Okay, so it has to be bound. It has to be bound somewhere. So this little thing here, eventually, this cholesterol, yeah, in this case here, what you're talking here is that this lipid droplet contains cholesterol. It has to be somehow going inside, and from this inside, it can turn into progesterone, cortisol, whatever the heck you want, depending on the enzymatic machinery of the cell. The other thing is that once, and let's say this lipid droplet here didn't just fall into the cell from the outside. It had to be transported with something. So the stuff that you're saying about the protein and peptides is the opposite. It's hydrophilic. So in this case, sometimes and lots of times they also have binding that they're transported bound. But lots of the protein ones, because they're hydrophilic, they can be transported free. Doesn't necessarily mean they are active, but they can be free, in there. Now, so solubility is a big deal. This is lipophilic. It has to be associated with something in blood. And then here, what you call here, the reason why I put it that part in the protein affinity versus capacity is that you have lots of proteins in your blood. You probably have heard about albumin. Albumin is super important for, to maintain water inside of your vessels. So you have to have quite a bit of protein in order to do that. Remember, you have hydrostatic pressure. You have some, sometimes they call colloidal pressure, or pressure that is caused by proteins to actually suck water from the interstitial space towards the blood vessels. So that kind of thing, it is important, or to go back to the affinity and going back to albumin, is that some of these hormones, now going back to the endocrine, are transported in several forms. A little bit is free, the majority will be bound, especially in the case of steroids. Some of them, they have very, very specific. Cortisol, you have one protein called transportin that is specific for cortisol, corticotropic, some other corticotropic hormone. And you have also albumin. The only difference is that albumin, you have lots in the blood. So even if the affinity is not very high, you end up transporting a lot of your cortisol with albumin because of the amount of it. Now, why and what the hell, Ronaldo, you're talking about this, in this specific class? Because depending on the problem that you have, even if it is not specific, you may unintended affect a certain system. So if your liver stops producing albumin, it's not only pressure things that will go off inside of your body. Transport of stuff will go off. Like will go into a banana-like mode. Meaning you're probably going to have, and this is one of the reasons why when you see people with one problem, especially some of the hormonal ones, they have to take like 5, 6, 7 pills. They have to take like lots of medicines because one thing is to treat the actual disease, but the other 6 is to treat the other things that disease caused that is unintended. Transporting capacity for some of these things are super one of those. Okay, so this is the stuff is not how we're gonna go to this. Like the previous one was hormone transport. This one is more hormone metabolism. Some of these names here, conjugation, reduction, this is basically what your liver does. You conjugate with something, you reduce that molecule. That's how you metabolize something. You go from an active hormone, passes through the liver, you conjugate, you reduce. That hormone then now has some other different structure because of that, and because of that, for the most part, becomes inactive. Okay. In some cases, what happens is that metabolization actually causes the hormone to become even more potent. The hydrotestosterone and estrogen are two examples. One is the metabolization of estrogen, or certain types of estrogen, the other one from testosterone itself. So which basically means that one will have to be metabolized again at some point in order to lose function. And this thing, hormone relative, like the metabolism of the hormone relative constant, is something that in some, this is one example of steroids and blood flow. So this is a big theory in why certain categories of animals that have poor reproduction is not because the repro system is bad, or partly it is, but other than that is because everything that controls the reproductive system is metabolized so quickly that you have much lower levels of those hormones than what is probably, or what would be probably ideal. So the cause of that was not even functional in terms of how the actual tissues can work. It's just because the flow of blood through the liver is so high and you metabolize so much that you end up having not much left over inside of the body. So what I want to do you get it? Where do I want to go with this? Metabolizing, transport, excretion, those things, keep those things in mind. Okay, so this is feedback control. Not much need for to go through that. You guys have a pretty good idea of this. Yes, target organs, releasing hormones, pituitary, hypothalamus. Yes, hypothalamus, pituitary, and whatever target organ. In almost all cases, you're going to deal with that. Okay, so hypothalamus and pituitary. Eventually, the names of the hormones and how it acts, if it is in the anterior pituitary, posterior pituitary, you're going to probably face some of those names. And the part is hypothalamus, pituitary, anterior, posterior. These are the two most important parts. This is really the organ that connects. I think that's the important thing. We talk a lot about the hypothalamus, for example, in our repro class. It's just because it is this central system that controls all the way from hunger to temperature to reproduction to water intake, you name it. Lots of the controls are there. This big portion of the base of your brain, the center of your brain, is really surrounded what we call the third ventricle of your encephalus, of your diencephalus, or your brain, the actual major part of the brain, and that's where lots of those things. And the reason why one thing affects the other is because they're all close together. So the neurons, they communicate with each other. So this is basically what it is: hypothalamus, anterior pituitary, posterior pituitary. This is actually a slide that I should have had in the repro class. Makes more sense than this one. But anyway, you got the picture. Some of these, like the thyroid, adrenal, pancreas, and so on, why did I put those in here? I think it is a little bit of why I mentioned that things on the table before, and then we went over a little bit, and you just added those 3-4 slides later on because I felt like, I think it is good to have a little bit of material on those. But the 3 slides, they go into this. Is it super important that you know that, the medulla is from a neuroectoderm origin and the cortex is from a mesoderm origin? Not the type of stuff that I'm going to ask you. Is it important that you understand that inside the same gland, you have very different responses? The adrenal is one of those. The adrenal gland, because we're going to talk fairly a lot about the adrenal gland, you do have this little guy that, if you open the adrenal gland, the cortex and the medulla almost look like 2 different organs. They have completely different functions in what they produce. The type of molecules that they produce are very different. So it's not like the hypothalamus. Almost everything that hypothalamus produces are what? Polypeptides. Almost everything that is transmitters are amines. Almost everything that for example, your gonads will produce, the great majority will be steroids. When it comes to the adrenal gland, the medulla produces amines. The cortex produces steroids. One is controlled basically by direct relationship with the neural system. The other one is a classic endocrine organ. So you see, it's almost like this. It's one inside the other. But they both are somewhat related to stress. Only stress? No. But if you want to, for example, nail your adrenal glands into 2 major functions, one is stress, the other one is energy. This is the part that sometimes, especially for these, especially here, the epinephrine, or we call it catecholamines. Epinephrine and norepinephrine, you can also call interchangeably with adrenaline or noradrenaline. Those are the same molecules. And both of them, not both of them, but a big portion of the corticoid especially, this aldosterone will be related to this, and cortisol will be what we call a glucocorticoid. But also the epinephrine works on glucose metabolism. Of course, you don't call it glucocorticoid because it's not a steroid, or it's not a cholesterol-based hormone, but it does affect energy metabolism. And this is one of those things that, as you mention treatment, or how you solve some of the problems, or how you, when you talk, for example, even in diabetes, that you're dealing with energy metabolism, you're going to see that they all play somewhat similar roles, but you're going to have, if you want to treat them, you have to use a little bit of one, a little less of the other. So this portion here, it's adrenal gland. It's important that you understand really well where things are, what it produces. Endocrine, in the sense of the pancreas, insulin and glucagon, again, hyperglycemia, normal glycemia. Those are by far the 2 major controllers, for example, of glucose metabolism, not necessarily tied with a stress response. Okay? They'll be the ones that, insulin, that very classic function of insulin, that what? Insulin causes blood sugar to drop or to go higher. Drop. Okay? Why? Because it allows the entrance of glucose to inside the cell, inside the tissue. Glucagon does exactly the opposite. It takes some of your energy reserves normally in the form of glycogen, and promotes the opposite, because your glucose levels have to be at a certain level. So water, pressure, CO2, O2, some of the minerals, sugar. if you think about, we already covered 5 or 6 things that is going to be extremely important for any case that we work in. They will have to be into a certain normal level. The other ones we talk about why. You know, so you talk about temperature, yes, of course, O2 and CO2, especially O2. We nibble a little bit on the acid base because of the CO2. And now glucose, for example, pressure because of the idea of diluting things or spreading everything that has to be changed between the vascular system and tissues. And glucose. Why do you have to maintain a certain amount of glucose in your organ or circulating? Oh, it's hypoglycemic, I'm gonna die. Why? Why do that?
Only energy your brain can use?
Yeah, that's exactly it. You know, the major reason is that it is by far, like the brain can use a little bit of some other sources, but it's like by miles. Glucose has to be the one. And your brain, especially when active, I think you have heard this story, it consumes somewhere between 25 and 30% of all the glucose that you produce, that you consume. For a mass of, I don't know, the human brain might have what? 1.5 kilos, maybe not even that, or 2, whatever that is. For the size of that organ, it is a super, super high consumption. So the idea is that, yes, your computer inside of your body only depends on glucose. So you have to maintain a certain amount. The other organs in your body can shift. It can go from glucose to what are the other energy sources in your body? Fatty acids. What else? Almost everything that has a carbon skeleton, theoretically, eventually could, not everything, not 100% of things, but can, through biochemical process, can proteins be used as energy? Can. Fatty acids, a lot. You know, it can pack up a lot of energy from those, especially those large, you know, long chain fatty acids. So the idea that in one you can, and the other tissues you can't, it basically means that the brain will be your rate limiting factor. So you're going to have to keep those in. So in this case, every time you eat, generally speaking, you're going to metabolize that food, not metabolize, you're going to digest that food, that food will pass be absorbed, pass through your liver, and your liver will really try to metabolize all the way from fatty acids to proteins to your fruits. And so right after your meal, your blood glucose goes up. In order to maintain the normal glycemia, what we call, your pancreas will do, among other things, excrete what? Insulin. We will bring those glucose to inside the cell. If you eat too much, what happens then? This is one of the things I say this, what happens then, because you know certain things in your body you can store, certain things in your body you cannot store. Okay? So certain things you can say, okay, so you consume too much cake. Eventually that cake will come in. Some will be used for energy, for the metabolism, or for the use of your body. The other part will be stored. Big bellies. Okay, so you're going to have adipose tissue going or coming from that. In the case of amino acids, what does it happen? What do you do? If you eat too much meat, Some of that will be used to for protein production, for amino acid production, repairing muscle, whatever, you know. Do you become stronger, more muscle cells, if you eat too much protein? Well, if you stimulate your muscles, maybe, but not to the point of using it all. But what do you do with the rest? Sorry. We're going to have a break, so but this last one. So you see how we go into very, very, I know it's not something that you need to know 100%, but let's see where that goes. So what do you do with that? You pee. Most likely, you're going to metabolize somehow, and eventually you may use your carbon. You know, some of that can even be stored because you can deaminate some of your amino acids. You remove the amine group, the remaining sometimes they start looking a lot like energy sources, either a fatty acid or glucose even. Okay, but the rest, that amine group, you're going to pee that eventually in the form of that will be converted to ammonia, urea, and you pee. So you see those kind of pathways, bigger picture pathways, and so on, is what is going to make you very creative. Again, that's the stuff that I want you to. I know you're very tired of me saying this, but this is what the more you know about this basic stuff is what will allow you to elaborate more in the case study. You're going to be more like you're going to have more tools to go with. That's okay. That's less. This is way more important. This one here just shows a little bit more. And so when we get back, so I said again, I don't want to extend myself too much on the endocrine side, but most important things, get to know a little bit of some of those major energy and metabolic and mineral hormones. Be more, I think this is the part, be more concerned with how it metabolizes, how it is transported, what kind of actions you have. And this last case here where we talk about if there is among all of those, the hypothalamus, the adrenal, perhaps the pancreas, for this side of it, it is one that the more you know, the better. We're going to probably go back and forth. We're going to be tired in the course, but it's going back and forth because it is really central to lots of cases. Okay? Very good. So let's have a little break. Oh yeah.
So I used the ReproLab account to get into it. And we're missing the beginning, but we have.
That's okay.
I'm on the Skype call.
Oh, is that right?
Yeah. I'm connected, but.
Okay, yeah, that's fine.
But I'm gonna just post the links to Canvas.
Nice.
So that way.
Awesome.
And I'm doing it for both classes.
Okay.
You're shutting it down. Okay. Like he was here.
Okay.
Yeah.
Yeah, this is one thing that maybe, not that for now, that's
Yeah.
awesome. I think one thing that maybe see how that can go, because I can do this the same next year, is I think too. I'm trying to get something to start writing more, to explain concepts.
Yeah. Oh, yeah, he need like a tablet.
Yeah, because that I think would be super nice to,
Yeah.
you know, to.
And then even like, cause that was just the beginning. So it hadn't synced with the camera yet, but this is how it views, so they can also see you. So if you're like pointing or something, then they can also see that.
Oh my God, it's almost over. Okay. Let's restart there with the digestive system. This portion here, of course, we'll try to be a very high level kind of review, the same way we did with the circulatory and the respiratory. A few things I think from the clinical standpoint for the digestive system, I think will be important in our case, will be that yes, it is this ginormous tube that goes inside our bodies tied with a bunch of glands, such as the own stomach produces certain kind of hormones, the pancreas, the liver, all of those are tied. And the immune system, of course, it concentrates heavily around your digestive tract for obvious reasons. The stuff is like all the things that we were saying that goes all the way, being this large tube that will actually digest and absorb, some of these nutrients. It means that the first thing, going backwards, the things that can go wrong will go all the way from you're not able to actually digest or absorb. Okay. The other one is infection, because you're dealing with too much stuff from the outside flooded inside of your body. And another thing is that this tube, more than any other place in your body, will be subjected to, if your digestion goes smoothly, you go digest, first you break down mechanically, after that you break down chemically, you absorb, and so on. The remaining material will have to go probably, and water, of course, you're going to have to absorb a lot of water through this. But even when things go well, you're going to have to get rid of that remaining material. In this case, in the form of feces. A portion, and when things go wrong, the problem is that if you don't, for example, digest the maximum you can, all that material that you ingested, something might happen, or not might, it will happen to that, which is, for the most part, and this is something that is central because of different species that we use, but generally speaking, you have no or very low tension of oxygen inside of your organs. In this case, inside of the tube of the digestive system, you do not have that much oxygen. So basically meaning you're going to cause some type of fermentation there. Is all fermentation tied with the presence of oxygen or absence? Not necessarily. You're always going to have some bacteria that will act upon that food. However, you're going to have something going on there. In some species, this is exactly what you want. Okay, so for example, in the case of ruminants, you're going to have lots of fermentation occurring before you even try to digest everything. Okay. In the case of some other species, such as the rabbit or the horse, you have quite a bit of fermentation in what we call the hindgut, or in portions of your intestine, and you still can use some of that either for energy. The problem becomes when whatever distortion occurs during the digestion process, and you end up having things accumulated inside of your intestines or your stomach, and that can cause trouble. Either because, and it can cause trouble by, in many, many ways. One that we normally associate with when, indigestion occurs. What is one of the things that you feel? Gas. So, and And along with gas, normally comes a little bit of pain, okay? Mostly because your organs, especially your intestine or your stomach, dilates. And this sort of movement for your organs, especially tube-like organs, is what causes lots of pain. The second part, so then one is like gases. So when you say gases, dissect that to me. What is this gas? What is occurring there for gas to be produced? It's fermenting. It's fermentation. So one of the things that happen to fermentation is that you change a lot of the stuff. So the thing is, a little bit of fermentation will always occur, and it's not necessarily bad. Thinking that it is. In the case of the rumen, you wish it happens a lot, and that's why a cow burps a lot, and that's why. But it is necessary because it can ferment or can digest things that the cow can't, such as cellulose, such as plant wall material. However, the problem then becomes, if you think about some of these things, it provides all this. If you cannot absorb this, it becomes a problem, of course. In this case of the functions, the digestion, absorption, but these portions here, once you cannot do or you leave things over in there, let's say fermentation. We were just saying that fermentation will occur at a rate that you don't want it. It produces lots of gas. You have to get rid of the gas. The other part is when fermentation occurs, this is the part where we go back to the basics. What is fermentation? I know we're talking about digestion, digestive tract, but this is important because it is a debate. Like this kind of rationale is the basis for it. Once, let's say you don't digest because going backwards a little bit, you can cause lots of fermentation in your digestive tract, either because you don't absorb, sometimes because you don't digest, which causes non-absorption. Sometimes it's because the motility is bad. So one of the major things in the digestive tract is that you basically have to keep things moving. And it has to be moving at a certain speed. It cannot be too fast, otherwise you don't even digest and absorb. It cannot be too slow, because if it's too slow, for whatever reason, you may go into this also effect on the fermentation or unnecessary or prejudicial, kind of fermentation. So again, now we can go. Now we understand why some of those things are there, the functions, and where it can go wrong and why. So in the case of fermentation, what is one of the things what is fermentation and what does it do? We have 2 minutes. Fermentation, in general, is the way in which certain organisms can produce energy. We have cell respiration, very efficient way of producing energy. Bacteria will normally they cannot do this, they don't use oxygen, and in the absence of oxygen, you end up doing fermentation. You can produce energy, yes, at a much more inefficient way compared to cell respiration, but you can. In both of those cases, you almost always will produce, on top of the energy, you end up also producing lots of what?
You get CO2.
You get some of that. You get some other gases too, methane, for example. But you tend to produce, certain types of acids too. Okay? So normally fermentation is also tied with, lower pH. You lower the pH because as you ferment, what happens to your bacterial population? You're fermenting, it means that the bacteria is using that. As it is using, grows. Okay? And it's producing there, blah, blah, blah. Eventually, let's say, so this is the bad part, to produce lots of gas. You can have a disturbing process there where you have much more of a certain type of bacteria that you don't want to have it. Okay? And the other part is that you start producing certain or end products that you wouldn't like to have. And eventually, also, what it might happen, that bacteria might start to, once the food is over and everything is fermented, that bacteria will do what? Yeah, but first, it's going to do what? It's going to die. Once you stop providing substrate for the bacteria will live off of nothing, you know, and then you start dying. And then you're going to go into the, you know, tied a little bit with our microbiology class. Once you have that, and you have to think of that in a more dynamic way. Basically speaking is, as you start accumulating things inside of the digestive tract, the dynamics of fluid absorption and what is retained and what it goes inside, and the one thing that you said, you know, you start saying, even the integrity of that tube will be compromised. So when you think about, I think that the nice thing about the digestive tract, think about very common things that, you know, are disorders, either vomiting or diarrhea. Vomiting is a bit more straightforward because it's just something that didn't go well in the stomach, or you have something that you ate that provokes that, you know, that anti-flux, you know, mechanics, and then you vomit. However, in the diarrhea side, you're talking about this something that did not go wrong. Eventually, you start having more things moving, perhaps a little faster, but at the same time, you can have lots of damage to the epithelial lining. You normally have what with diarrhea? You go a lot of water. Almost like one thing that, you know, people don't pay attention to this, but diarrhea and vomiting, one of the very first things that you have to take care of is hydration. It's lots of water that you didn't absorb, and in many cases, it's water that actually have to come from your system to the lumen to control or to equilibrate something, you know, inside of it. So the next slides, and we're going to have to stop now, but the next slides will be a little bit about some of these controls, a few things that will have to happen there, but also about the basic of the anatomy and what happens to the movements. You know, movements have to happen in a certain way in order for you to not only digest, but there's a big concern of the digestive tract to actually, between meals, to remove everything. You know, when you're hungry and you start having those sounds, you have those, this is a certain type of sound. It's a certain type of movement that exactly happens in between meals. The idea is that normally your intestines, they work like in pockets. They concentrate, digest, absorb, and move. So your things, it's not like a free flow thing. It works like, especially in the digestion side. And eventually, when that happens and you stop eating, the intestine tries to do what? Almost like clean up everything. Why? Because this idea of leaving material behind and causing fermentation, it is a big deal. You start producing things that you're not supposed to be producing. Okay? So in the digestive system, you're going to have to be tied eventually with, obviously, with endocrine and other things, but there is a very, very important mechanical side to it. Okay? And that is also tied with osmotic control, water coming in and out, food being produced or not, food not, and energy being, how energy is produced from that thing that is absorbed. Okay? So, quiz will be next Thursday, first one. Probably by Tuesday we should finish with this, so we will cover, I'm pretty sure we might be able to cover the two classes for this first one. And that's it. If you have any questions, please write me.